Good morning. This is Mr. Allen, and today we're going to look at section 9.3, which is on parametric equations and calculus. Share my screen again with you. Okay. All right. First thing you'd probably like to know how to do is how do we find the derivative of a parametric equation. So here we have a parametric equation. We want to find its derivative. So the definition of the derivative is simply dy or dx is equal to dy over dt divided by dx divided by dt. In other words, it's going to be a fraction with the derivative of the y component on the top with respect to t, and the denominator is going to be the x component with respect to t. So for the y component on the top, the derivative of y equals cosine t. Well, I think that's going to be negative sine t. And for the bottom, I'm going to do the derivative of the x component with respect to t, and that, of course, is cosine t. Therefore, sine over cosine is tangent. So dy dx for this particular parametric equation is negative tangent t. So this will give us the slope of the tangent line for this particular equation for any values of t. Oops. Okay, example 2, we're going to talk a little bit more about slope and concavity. So here's a little bit more complicated example. I'm not going to show quite as much work, but you got your x components of the parametric equation, the y components, and the domain here is t greater than 0, which you can probably understand why that is based on the x component. So the derivative, and I'll kind of let you guys, I'll write it this way. You can say it's, you can say it's the y component with its derivative with respect to t, and then the x component with its derivative with respect to t. And in this case, I'm going to kind of jump ahead here. So I'm not going to show all the work. This is going to be t to the 3/2 power. So I would encourage you to work that out and make sure you agree with that. Now we just need to evaluate this derivative for the point t equals, or x equals 2. So if x is equal to 2, then t would be equal to 4 based on the definition we have here for x. So if I put 2 in for x, then clearly that's going to be 4. And remember, we're restricted to just t greater than equal to 0. So our final answer here is going to be 8. So the slope of the tangent line at 2, 3 is going to be 8. We also want to look at the concavity to find the second derivative, and I think I may have written this incorrectly on the notes. To find the second derivative, which this is our normal notation here, it is simply going to be the derivative with respect to t of dy dx, which is what we just found, divided by dx dt, which is this denominator up here. The numerator is going to be the derivative of t to the 3/2, so that's going to be 3t to the 1/2. Sorry, I'm trying to use a stylus here and it's just not writing very well. Let me fix that. Let's see if I can fix that. Okay. All right, let's try that again. So it's going to be 3/2 t to the 1/2 divided by what's going to be just the derivative of x, which we already know is 1/2 the square root of t, which is equivalent to x. And when you clean this up, it all becomes 3t. Then we want to go ahead and evaluate this again at t equals 4. And that's going to give us an answer of 12. And remember, we're talking about the second derivative. So this 12 is greater than 0. So therefore, this guy is concave up at 2, 3. All right, I'm going to go a little bit faster here. I think I'm going to, I'll do this example, but I'm going to do it kind of quickly. So we can clearly see that our parametric equation is this curve drawn on the graph. You can see the arrows indicating the motion. We're trying to find the equations of the tangent line. Hopefully it's clear that those tangent lines are symmetric. They have some symmetry properties. The tangent line turns out to be at t equals pi over 2, which in terms of our regular coordinate system, that's the point 0, 2. And I'll let you verify why that's the case. But to find the equation of the tangent line, of course, you need to find the derivative, which again is going to be y component with respect to t derivative, x component derivative with respect to t. And in this case, you're going to get pi over pi sine of t divided by 2 minus pi cosine of t. Then we need to evaluate this at t equals pi over 2 for the reasons I mentioned over here. And this turns out to give us an answer of, coincidentally, pi over 2. That's our slope. And we already know that the x component and the y component is 0, 2. So the tangent lines are y equals plus or minus pi over 2 x plus 2. Those are the equations of those two tangent lines. All right, last example is going to be based on our formula here for arc length of a parametric equation. Again, this dx dt, I will note that as x sub t, and dy dt can be denoted as y sub t. So if I want to find the arc length of this curve from 0 to 4, we are simply going to use the formula on the previous slide. We are going to integrate from a, which is 1, b, which is 4. Then we have to do the square root of x sub t, so the derivative of x with respect to t. So that's going to be 12t, but then we got to square that plus the derivative of y of t squared, so that's going to be 6t squared, and all of this with respect to t. And the answer will turn out to be 156.525. And that is that. Thank you very much, and I hope that makes some sense.